Let us solve one more problem regarding the characteristics of DC shunt motor before we move on to the next topic. For this, let us assume a DC machine when operated as a generator at 1000 rpm, DC shunt machine, gives a terminal voltage of 250 volts. The machine has a armature resistance of 0.5 ohm and a field resistance Rf equal to 250 ohm. Now, at no load, when supplied from a motor operated as a motor and supplied from a source of same 250 volt, the armature current drawn equal to 4 amperes. The current drawn from the supply is 4 amperes. Now, I load this motor up to a IL equal to 40 ampere, supplying from same Vt at load equal to 250 volt. Suppose it has been found that delta phi F due to armature reaction equal to 4%, just as we found out in the previous problem. Now, we are expected to find out the speed at the above load and the efficiency of the generator at load. How do we proceed about this? First, let us try to find out the generated voltage at 1000 rpm when run as a generator. So, this machine was run as a generator at 1000 rpm as a shunt generator. This is Rf equal to 250 ohm, and when run at a 1000 rpm, the generated voltage was 250 volts. This being a shunt generator, in the generating mode, this current Ia equal to If and IL equal to 0. So, under this condition, since the generated voltage is 250 volt, then Ia equal to If equal to 250 volts by 250 ohm, this is equal to 1 ampere. So, under this condition IaRa equal to 0.5 volt, since Ra equal to 0.5 ohm. So, the generated voltage E at 1000 rpm equal to 250 plus 0.5 equal to 250.5 volts. Now, let us try to find out the no load speed when this machine is run as a motor. This is the generator. is again supplied from a 250 volt supply, the same field winding of 250 ohm resistance the load current drawn is 4 ampere. So, let us try to find out what is the no load speed. So, I f is again 250 by volts by 250 ohm, that is 1 ampere. I L at no load equal to 4 ampere. So, I A 0 equal to 4 minus 1 equal to 3 amperes. I A 0 R A equal to 1.5 volts. So, E 0 equal to 250 minus 1.5 equal volt equal to 248.5 volts. So, what will be no load speed? N 0 is proportional to E 0 because field current is same. So, N 0 by 1000 rpm equal to E 0 by back EMF at 1000 rpm, that is 250.5 equal to 248.5 minus 250.5, which is equal to so N 0 from here we get as 992 rpm. So, at load condition are again supplying from a 250 volt source. The load current drawn I L equal to 40 ampere, this is still 250 ohm. So, this is I F equal to 1 ampere and I A equal to 39 amperes. So, what is E under load condition? 250 minus 0.5 into 39, this gives you 230.5 5 volts. Now, E by E 0, E is proportional to k phi n. So, E by E 0 equal to phi at no load n 0 by phi at load condition by n. Now, it is mentioned phi equal to 0.9650 due to armature reaction. So, n equal to E 0 E by E 0 into phi 0 by phi into n 0. This comes to 958.5 RPM. Interesting to see that if phi 0 and phi would have been same, then speed drop would have been more, because this quantity is larger than 1. Phi 0 by phi is equal to 1 by 0.96. So, how do I find out the efficiency under load condition? The developed mechanical power under load condition P m developed equal to E into I A. This is equal to 230.5 into 39 so many watts. What is the mechanical loss? Now, at no load we see that the armature current is not 0, it is 3 amperes. What happened? But there is no load connected to the shaft, that is actually the mechanical loss. So, P m loss equal to E 0 I A 0. This is equal to 248.5 into 3 watts. So, the shaft power output by efficiency equal to shaft power output divided by P electrical input. This is equal to V T I L. This comes as 230.5 into 39 minus 248.5 into 3 divided by 250 into 40. This comes to 82.44%. So, we see that we can find out, if the data is known, we can find out different performance parameters like speed, efficiency, current, etc. for a shunt DC motor. But before a DC motor can be used to supply a load, it must be started. How do I start a DC motor? Okay. The simplest approach will be to connect both the armature and the field to the available supply voltage V t. Well, this of course can be done theoretically, but this approach has some problem. Let us look at what the situation is. The torque speed characteristics of this DC motor looks like this. This is omega, this is T e, and to some scale also I a. Now, at start omega is equal to 0. So, what will be the torque? That will be obtained by extending both these lines. So, we can very easily see that at start there will be a huge current and a correspondingly a huge torque. This is obvious because at start the back EMF is 0. So, the armature current I a at start equal to V t by R a. Now, this R a is a very small value, because if we want high efficiency at loaded condition, we cannot have a very large armature resistance. For very large machines, this I may be as small as 1 per unit, 1%. The at for even small machine, it will not be more than 10%. So, you can expect anywhere from 10 to 100 times the rated motor current to flow if A is connected directly across the supply voltage. So, how to overcome this problem? If the armature voltage can be made variable, then of course, we can start with a very low voltage and overcome this problem. However, more often than not, only a fixed voltage source will be available. So, the next simplest approach is to connect a armature resistance in this manner. There are two resistances, one connected in the armature circuit So, with this during start we can write I a equal to V t divided by capital R a plus intrinsic armature resistance R a. So, by choosing appropriate value of R a, we can restrict I a less than the I a max. Generally, it is I a max will not be less than 200% of rated I a. Much larger I a is usually not acceptable, particularly for a DC machine, because as we know that a DC machine contains a commutator and brush arrangement. So, where there is continuous making and breaking of the circuit. So, if a very large current flows, there will be added sparking at the commutator, which may damage the commutator segments. Otherwise, even a very large starting current will also cause a very large starting torque, which may be detrimental to the mechanical system of the motor or its coupling to the load. Also, most supply system will not permit very large current to be drawn, as will be found if the motor is operated directly from the supply during start. So, we add a additional resistance to limit the current, but then what happens? Once we add the resistance, the motor characteristics changes. This was the intrinsic characteristics, and possibly this is the characteristics with the added resistance. This is possibly 2 times IA rated. But then we see that although at start the motor draws 2 times rated current, as the speed of the motor increases, the operating point moves along this line. So, as the motor speeds up, the current starts reducing. That way, the acceleration of the motor becomes slow. So, for the whole duration of starting, the armature current does not remain fixed. So, one approach is to use a variable armature resistance. So, if one use a rheostat, the armature circuit, and adjust the rheostat so that the as the motor speeds up, the resistance is also changed, so that as the motor speeds up, we keep changing the resistance, so that the current remains more or less constant at its initial value up to the point where it has almost reached steady state, but then I allow short the resistance, so that the motor comes to the normal operating point. This will be the ideal characteristics. However, in practice it is difficult to vary the armature resistance continuously, and therefore, sectionalized step resistance starter are normally used for DC motor starting. Another point that should be kept in mind is that before the armature resistance, the motor supply is given to the armature circuit, the field circuit must be excited first, because field has a large inductance in addition to the resistance of LF, and the current in the field will take some time to develop, and until and unless field current has reached its full value, the field flux will not reach its full value, and the back EMF, which is given by omega, will not reach its full value at a given certain speed at. So, it is necessary during starting to have the flux at its rated level, at the maximum level, so that as soon as there is some speed developed, some back EMF is developed, and the current flowing through the machine is restricted. So, the during starting, the field resistance must be completely shorted to allow maximum current to flow through the field circuit even before the voltage is applied to the armature. After the field current has been established, the voltage can be applied to the armature with the armature resistance at its maximum position, so that the casting current through the machine is limited, and then preferably the armature current should be cut out as the speed of the machine increases, so that the machine accelerates at within a reasonable time. However, as we mentioned that it is difficult to get a continuously variable armature resistance, therefore, step resistance starters are normally used for DC shunt motor starting. We will explain the working principle of one of them. Let us say this is the DC motor to be started. So, this is one of the armature terminals. This is the plus minus supply Vt. This is called the load terminal. These are the three terminals to which a starter is connected. So, what are the things in the starter? The starter consists of several sections of resistance. And a conducting and a handle to connect them. This handle is spring loaded. This load line is connected to this spring and to this handle through a electromagnet. One of this armature terminal is connected to the last point. This handle is variable, this movable with a external insulated shaft. So, these are three corresponding terminal on the starter. On the handle there is a soft iron piece. field winding is connected in series with the coil of another this is the starter arrangement. Since there are 3 connecting points on the starter as in the armature, this is called the 3 point starter. So, initially this handle is in off position. When we switch this on, switch on the supply, then first field circuit is excited, through this and through this line. When we put this on first and move this handle to this off position, the field circuit first gets excited and then armature also gets it supply. This is in this position. So, through this line armature gets the supply through all these resistances and the field circuit gets a direct supply and the machine starts accelerating. As the machine speeds up, the position of the handle moves to the next stud. So, this part of the resistance is cut out from the supply and the current in the machine increases. The machine accelerates further and the current starts reducing. When the current has dropped to certain level, the handle is moved to the next stud, then next stud and finally to the on position. When it reaches the on position, all the resistance in the armature circuit is cut out and the machine operates with its intrinsic armature resistance. There are 2 more protection features presented here. One is the so called no volt coil. This is the no volt coil. We see that this no volt coil is connected in series with the field winding across the supply. So, under any condition, if the field circuit is broken and no current is flowing through the field winding, then this soft iron magnet, this permanent magnet, this electromagnet gets de-energized and it releases this soft iron piece. Since the handle is spring loaded, immediately the handle reverts back to the off position. So, the connection to the armature supply is disconnected. That is how the armature is protected from accidental opening of the field winding. In addition to this, there is also a overload coil which is connected in series with the load line. So, as long as the load current is within the permissible value, the pull of this electromagnet is not large enough to attract this plunger, but when the load current increases to a very large value, then this plunger is pulled, so that the contact here is closed, which shorts the no volt coil, and hence the starting arm is released and the machine turns off. So, this commercial 3-point starter provides step resistance starting and also protection against accidental opening of the field winding as well as over voltage over current in the machine. However, this is a manual starter. These days most of the semi automatic or automatic starter are based on relay contactor principle, which can be schematically represented like this. Let us say this is the armature, there is a main contactor and of course, these sectional resistances. Each part can be shorted using a contact. And the field coil is connected directly across this. And this is where the supply is given. Is the main contact. These are the starting contacts C1, C2 and C3. There are 3 sections of resistance R1, R2, R3 given total resistance of, when all the resistances are in, let us say the resistance is R1. When C1 is shorted, the resistance becomes R2. When C2 is shorted, resistance becomes R3. When C3 is shorted, the resistance becomes R4, which is nothing but the armature resistance of the machine. Now, in addition to this simple scheme, of course, many protection features like no volt release, overload protection, etc., are also provided with commercial relay contactor based starter. So, when you push a start button, first the main contactor closes and the machine starts accelerating. After certain time, when the machine current falls below certain limit, the first contactor closes, the current immediately jumps and torque increases again. After some time C2 closes, after some time C3 closes, so that the machine comes to full speed. Pictorially, the current and speed variation can be represented like this. This is the armature current IA, this is time, and let us say this is how the speed looks like. So, initially when machine is started, the current jumps to a value I1, the machine starts accelerating. As the machine accelerate, the currents drops, and at this point let us say the first contactor C1 is closed. And let us say by that time the current has dropped to a level of I2. So, here the total armature circuit resistance was R1. As soon as C1 closes, the current again jumps back to I1 and starts acceleration again. Here it will be R2. Once current again falls back to I2, C2 is closed and current again jumps back to I1. So, here it is R3. Finally, here the last contactor C3 is closed. Initially the current jumps and then settles to its final value. This is how the armature current and the speed variation looks like in a sectional starter. This is R4 equal to RA. Now, how does one compute the values of the resistance to be inserted in the armature circuit, so that the current waveforms during starting looks like this? For that, we note that the total resistance, when the total resistance is R1, then at start I1 equal to V by R1 at time 0. At time t1, the current drops to value of I2. So, I2 equal to V minus E at t1 divided by R1, but at the same time we are shorting the contactor C1 and the total resistance is becoming R2. Since the back EMF depends only on the speed and speed cannot change instantaneously, we can also write I1 equal to V minus E t1 by R2. Therefore, from here we have I1 by I2 equal to R1 by R2. And in the same manner, if we continue for K section resistance, we can induce that I1 by I2 equal to R1 by R2 into R2 equal to R2 by R3 equal to R3 by R4 for K section resistance. And finally, R k minus 1 by R k. For K start, that is K minus 1 section of external resistance. So, there are K such terms. So, I1 by I2 to the power K minus 1 equal to R1 by R2 into R2 by R3 into R3 by R4 into Rk minus 1 by Rk equal to, these things cancel, it becomes R1 by Rk. So, if there are k minus 1 external sections, then Rk is the last resistance, that is equal to Ra. So, we have, we define I1 by I2 equal to some gamma, then R1 by Ra equal to gamma to the power k minus 1. Now, R1, if we, so the process, design process goes like this. First we choose given value of I1 and I2, then we find the value of gamma equal to I1 by I2. In order to restrict the starting current to a value of I1, we choose R1 to be equal to V by R1, R1 equal to, sorry, R1 will be chosen as V by I1. Now, we know gamma to the power k minus 1 equal to R1 by Ra, or k minus 1 ln gamma equal to ln R1 by Ra, or k equal to ln R1 by Ra divided by ln gamma plus 1. So, that is how we find out the number of sections needed. Of course, we have to make sure that we choose the a nearest integer to what we get from this formula. Once number of section has been chosen, then of course, we can always find out the resistances from the relationship R1 by R2 equal to R2 by R3 equal to R3 by R4 equal to, this way, R k minus 1 by R k, which is nothing but R a equal to gamma. So, R k minus 1 equal to gamma R a. So, the first sectional, last sectional resistance can be find out, which is R k minus 1 then equal to R a plus small r k minus 1. So, small r k minus 1 equal to R k minus 1 minus R a. This way it will continue till we find out all the smaller individual resistances. Let us try to explain this with the help of one problem. Let us say we need to design a starter for a 220 volt DC shunt machine. The maximum current I1 should be limited to 55 amperes and the minimum current during start 2 should be limited to 35 amperes. So, find out the number of sections and the resistance in each section. Let us say R a equal to 0.4 ohms. Then I1 by I2 equal to gamma equal to 1.57 and R1 equal to V by I1 equal to 220 by 55 equal to 4 ohm, gamma to the power k minus 1 equal to R 1 by R A, which is equal to 4 divided by 0.4 equal to 10. Hence, n equal to k equal to 6.1, or the nearest integer is 6. So, it has to be a 6 step resistance. This modifies gamma to a value of 1.585. So, we have R 1 equal to 4 ohm, R 2 equal to 4 divided by 1.585 equal to 2.52 ohm. So, small r 1 equal to r 1 minus r 2 equal to 1.48 ohm, r 3 equal to 2.52 divided by 1.585 equal to 1.589 ohm. Hence, small r 2 equal to capital R 2 minus R 3 equal to 0.931 ohm. In the same manner, we can proceed and find out R 3 equal to 0.587 ohm, R 4 equal to 0.370 ohm, and R 5 equal to 0.235 ohm. Instead of specifying the maximum and minimum limits of the currents, it is sometimes simpler to specify the number of steps, but there basically the same relations hold. So, when the number of steps are specified, we still have the basic relationship gamma to the power k minus 1 equal to R 1 by R A, and R 1 is still equal to V divided by I 1. So, the maximum current will be specified and the number of steps k minus 1 will be specified, from which we have to first find out what should be gamma and then proceed in the same manner to calculate the different starting resistance sections. Thank you.